Okay, so today we're going to start talking about files. So we sort of skipped over, at least for now, I/O devices, like the actual underlying hardware management part of this. In my opinion, the sort of learning about file systems and how files work is a little more integral to an OS course. So what we'll do is we'll spend a week or two on this and learning about files and file systems, and then probably like the last week or so of the course, the last few lectures will be based on what you want to learn about from the last few topics in the book. So basically we can jump back and talk about storage management, we can talk about security and protection, or we can talk about some of the advanced topics like virtual machines. So I'll at some point I'll post a poll on Piazza and see what you'd like to learn about, because we've sort of gotten through, once we get through files, that's like the meat of the OS course. We may have a little bit of extra time to learn about some other stuff, so I'll kind of leave that up to you, what you'd like to learn about. So today we're diving into files. There won't be a reading quiz for Tuesday, because I think or for Wednesday, I think I gave a little too much to read, more than what we'll get through today. So you'll be done for the week for that at least. So we're talking about file systems, which provide collections of files and the directory structure. So it's these two things. And a lot of the operations that we're going to talk about today have some amount of manipulating both of those things. So the files themselves are, a structure that links to the storage that we have. So whether that's a hard drive that has a disk that spins, and we have to decide where on that magnetic disk we want to write this file, or that has, a more solid state setup where, we have this RAM essentially that is non-volatile, that we choose what address to write to. In any case, we have, this set of files that are basically just bytes on some storage medium. And then we have a directory structure that is sort of the user view of files. So the collection of files is kind of the system view. That's what the hardware has and what the OS is showing us. The directory structure and the file names are what the user actually sees. So the OS abstracts the physical properties of these devices to provide a logical view of the stored information in files. The files tend to be stored in non-volatile storage so that the contents are persistent. And from a user's point of view, a file is the smallest unit of secondary storage that can be used. So when we store something on our computer, we create a new file. We don't just, store a byte here and there. We have to make a file with the name and, all of the other stuff associated with it in order to store that on our secondary storage. So we don't really have a way of just directly storing a few bytes to the hard drive, right? We always have to make a file, and then that's the way the OS stores that on the hard drive for us. So a file is generally a sequence of bits, bytes, lines, or records, the meaning of which is defined by the file's creator and user, whether that's you or whether that's another program that you're using. So usually, and we'll talk about this a little more, the OS doesn't really handle the structure and interpretation of a file. It's another program's job to handle how a file is represented and what that file means. So to the OS and to the hardware, a .txt file is not that, or is not different from a .jpeg file or a .pdf file. It's up to the programs on the system to manage those files. I think the only place that gets a little murky is obviously your OS has some features for recognizing common file types to be able to launch a program or launch the program that handles that type of file, right? So when you click on a PDF, it opens Acrobat. When you click on a .txt file, it might open Notepad or something like that. A .doc, it opens in Microsoft Word, etc. So there is some amount of knowledge in the OS about file types, but for the most part, to the OS and the hardware, they're just sequences of bytes and the meaning is application specific. Okay, so files have a number of attributes that define common information. So we have names, which are the sort of user level view of a file, human readable format. So this is what we would call the file, not what the OS necessarily would call the file. The identifier, on the other hand, is the system view of the file. This is like some tag, a number that identifies the file at the OS level. Okay. These are two separate things, right? The name is the user view, this identifier is the system view. They're both associated with the file, but we probably never see the identifier. The OS does see the name just to be able to translate it to the identifier, but then from that point on, it's probably using a more compact identifier. So this way, we can give our files some, huge, ridiculous name if we want to, and the OS can map it down to a small number of bytes that can be used everywhere else in the system, so that it doesn't have to carry around this large string that might be a variable length, that might be, really long. It doesn't have to carry around that name anywhere except from like the file's description or within the file attributes. So it can map from the name to the identifier, and then the identifier is the thing that can be used pretty cheaply through the rest of the system. Obviously, we have file types. It's more user level view. Applications support different types of files. But at the end of the day, like the type is, again, it's more of a user readability type of thing, or usability type of thing, right? It helps us identify what common files are. It might help programs identify if they deal with this file or not. But at the end of the day, these are just bytes. So, you can make your own file types if you want to. You don't have to use the system-defined types. You can, it just has to be whatever the application you're using to run with this file or to parse this file has to know how to handle that type, but they don't have to be any particular thing, right? HTML files are just text files that have special markup in them. Likewise, most programming languages are just text files that have special types of markup in them. Location is a pointer to the file on the device. This is how we sort of unmask the underlying storage part of it. So the location is the actual place that this exists in the physical storage. So that might be an address in an NVRAM, non-volatile RAM like an SSD, or it might be a sector and location on a solid or on a magnetic disk, something that spins and rotates. This is just the OS way of dealing with the hardware for us, but something that we don't have to deal with as the users. So it doesn't really matter to us where this file is in the physical storage. We just have to know the name of it and where we want to be within that file, and the OS will handle the hardware details for us. Size is the current size in bytes, words, or blocks, and maybe the max size. So this is just tracking, making sure that we can, keep track of how big our files are, and how much space we're using up on that disk. Protection we've talked about a little bit before. So this is access control, like writing, reading, executing, and sometimes other attributes like hidden, for example. So you may see, a hidden file on your system. Usually on Windows, you have to, open up the settings and check a box to say show hidden files and folders. So hidden can, hide files from the user so that they can't even see them. But that if they do want to see the hidden files, they can read and write and execute them in some cases. So it's more of a like mild protection mechanism where it's sort of opt-in to hide the files that you probably shouldn't change on like a Windows system, that you might not be able to always see all the files, but as soon as you reveal the hidden files, you can see them. This happens on Linux as well. So like often things like the Git files, so when you use git clone or create a Git repository, that creates a hidden folder within the Linux system, within the file system, that is there, but you usually don't see it. So if you look in one of your repositories, you probably have a .git folder if you do ls-a that will show up. So let me open up actually terminal here and make this a little larger. If we do like an ls-l, we can see a lot of the stuff that we're talking about here. So you can see the name of the file. We don't actually see the identifier for the file. We'd have to look at the the proc system. So proc / some number that it may not let me do here since yeah, I don't have permissions. But if we can look at FD, no, if you can look at FD and FD info, you can actually see like the OS level identifiers for files for that running process, because it'll show you what files you currently have open. But otherwise, if we look at ls-l, we can see the file size here. We can see the last modified date, which is important for some things. So timestamps. See the owner and group of the file. We see, I think this is like how nested it is in a directory. And then we have the permissions for that file, which are read, write, execute, read, write, execute, read, write, execute for the user, group, and everyone for this system. And we can talk about that a little more when we get to security, but just wanted to sort of show it for now to show what this looks like. So most of this information is available. We can look at the same thing on Linux if we want to. So we can look at or on Windows. So like a random MP4 file from compilers this morning. We have very similar information on a Windows system. So we have the type of the file, what it normally opens with, location, size on disk, created, modified, accessed, some special attributes, and then we should have some security details here. And this has very similar stuff, which is like modify, read and execute, read, write, full control, etc. So very similar information no matter what system you're in, just different formats sometimes. And so then finally we have timestamps and user identification. So this might be creation, last modified, last used. And this is useful for protection, security, usage monitoring. This is also really useful sometimes as a performance optimization for certain applications. So if you think of things like Git and make, so when you build your programs and run the make application, this is a tool on Linux that builds applications based on some rules. One of the big benefits of make and other build systems like it is they can usually ignore things that you've already built. So I think Rupam can attest that whenever we have to build LLVM from the base up for compilers, it takes like hours to build because we have to build a lot of files. Some of the executables are very large, but most of the time it can be pretty quick. It just has to scan over the files, make sure that nothing has changed, and then build the ones that have changed and sort of propagate that through the rest of the tool chain. So timestamps can be used as an optimization if we can say that, okay, this file has not been changed. I don't have to do anything if that file wasn't changed. So let's just move on. Okay. Any questions so far on files? This is probably a little bit dry, the usual intro to a chapter. It's a lot of stuff that you probably already have some familiarity with since you've been using computer systems most of, if not your whole life. So I'm sorry if it's a little bit dry, but I want to make sure we have the background info before we dive into the more complicated stuff. So, okay, so we also provide common functionality for a lot of common operations. So creating a file requires 2 steps because of the fact that we have this sort of user view and the system view of the file. So we have to create space in physical storage for the file. And we have to create an entry for the new file in a directory. So this first part is, what we do for the fact that we have this storage on an actual physical medium, like a hard drive or an SSD. And then we have the user level view where we want to organize these files into a meaningful system, meaning that we want to create a new entry in that directory as well when we create the file. So we want to have the sort of user view of the the name and the system view that has an identifier in a physical location. Opening a file, usually this happens as part of something like fopen. Right? So you should be kind of familiar with something like this. That usually when we write code in C or C++ that uses a file, we have this process where we open it and then we pass around a handle or a pointer to that file to everything else, right? So we never really say like, we don't say write file.txt hello, right? We don't write to a specific file name and then say what we want to write to that file name, because that would be inefficient because we constantly have to like open the file, write to it, close the file, open the file, write to it, close the file. Instead, what the OS wants us to do, and so what abstractions have been built around this, is to basically, we open the file once, we close the file once, and we write to the file or read from that file multiple times once it's open. So most, if not all, programming languages that you use are going to be built around the same abstraction where we open the file one time, and then we get a pointer back to that file, and we use that pointer, or in this case we call it a handle, to access the file from there on out. So opens a file for operation and returns a file handle. That's sort of the key thing here. I like that. So we get a handle back, and then we can use that handle as an argument to other calls, and that's mostly how every programming language works, right? Even the higher level ones like Python and things like that, they're still going to open a file, give you a handle back, and then you can do things to that file handle. Okay. And we'll talk about a little bit later having multiple open files. Any questions? Okay. So writing to files, we usually keep a write pointer, and so we basically write to new data to the write pointer and adjust the write pointer. And same thing here, read data from the read pointer and adjust the read pointer. This allows us to, overwrite a file if we want to overwrite contents of a file, and or append to the file if we want to write to the end of it. We usually have both of these pointers so that we can do reads and writes arbitrarily from different places in the file if we want to. Sometimes it's useful to be able to, like, if I want to copy and paste, for example. I want to be able to read from some point in the file and write to another point in that file without, changing where I'm at on either of those pointers. So I can, copy a chunk from where I'm reading to where I'm writing, rather than having to, read from a pointer, move the pointer to the end, write to that same pointer. So it's convenient to have both of these if we can. And then repositioning within a file. I think we've talked about this a little bit previously. So this is also known as a seek. So this moves the current moves the write or read pointers to a new position, also known as a seek. We can look at like fseek plus reference. So this just repositions where we are doing things within this file. And we can, give basically where we want to go from, where we want to offset from that position, and then the file pointer, just like we would normally have. So this allows us to either go to the beginning of the file and then some offset from there, the end of the file, some offset from there, and or the current position where we can sort of seek back and forth. You can see here that this doesn't actually have a way to control these separate read and write pointers. So in the C API, we can only really go from one single pointer in this case. Okay, so that's seek, and that would be like, I'll just leave a reference here to fseek in case you haven't used that before. And then deleting a file, we want to search for the named file. So this is a little bit complicated because we may have links to a file. So this would be like a shortcut, right? And it depends on if they are hard or soft links to determine what we are going to do with that file whenever we delete it. So this is the way we make a link in Linux is ln. So ln takes in the most simple form, a target and a link name. So we say, I want to link to this file with this new name. So what this allows us to do is, for example, if I want to use, and I don't know if it'll let me do this or not, but I want to use user or bin ls as ls in this directory. And it's not going to let me. I can do a symbolic link if I want to. So I can create a new, let me move this up a little bit so it's easier to see. I have now created a copy of ls within my directory here. So now I can do /ls and it's the same program. And that's what ln does, is basically creates a link to the to a file that we want to link to. There are two different types of these links. So I'm just going to make this a sort of a bullet point here. A hard link is a direct copy of the file. A soft or symbolic link is a basically just a pointer to the file. This is why it wouldn't let me actually create the hard link of this without having -s, because this is a root controlled file. It doesn't want me to have an actual copy of it necessarily. So when we delete a file, we have to deal with the fact that we may have links to that file. So essentially, we have like these file names that we might have more than one of for the same actual file. And then underneath the covers, we have a hard copy on disk somewhere of the actual file. A hard link is a hard pointer to that if we delete the original file name, we won't delete the underlying content. So the hard link is essentially another copy of that file, even though it points to the same place on disk. A soft link, on the other hand, is a pointer to that if we delete the original file, the soft link will just point to nothing now. It'll be a dead shortcut that the program that we're trying to access, the file that we're trying to access through that shortcut, no longer exists. So to delete a file, we release the underlying file space if no hard links exist. We basically have to have some sort of a counter to make sure that we have actually deleted all of the hard links to that program, that there aren't any more copies of this exact file floating around on our system. Okay, and I'll leave a reference to LN here in case you want to look that up later. So that's something you run into, and I think it's like MK-Link on Windows. So Windows can also have symbolic and hard links to files, or soft and hard links to files. So we can have a direct copy of a file if we haven't modified it. It's it's the same. It's a different name and a different place in the directory structure for the same underlying file. Like if I have the same PDF in two different places, it's still the same underlying file when I access it. If I make modifications, then it's going to become a different copy of that file. And then a soft link is just a shortcut to that file. So every time you make a new, you add a new program to your system that says, would you like a shortcut in your desktop? Not a copy of the executable. It's just a symbolic link to that executable. Okay. And then truncating a file. This is, the user may want to erase the contents but keep its attributes. So rather than deleting it and recreating it, we allow all the attributes to maintain the same except for the file length. So resets the file length to 0 and releases the file's underlying space. And what you want to look at for that is ftruncate. This is the Linux man page for that. Load in a second, hopefully. Ftruncate. There you go. So we, in this case, either have a file descriptor that comes from the open system call and a length, or we have a path to the file and a length. So either way, we're just reducing this to a specific length. So ftruncate actually allows us to, instead of just zeroing it out, we can give a new specified length that we would like to put that file to, and it will truncate it to that size. If it was larger, it loses any data that was past that size. If it was shorter, it extends it with a bunch of null bytes. And it does not change the offset. So it does not change where we're currently reading from in that file. So we have to make sure that if we truncate something that we're not already out of the end of that file, basically. Okay. Any questions on this stuff so far in terms of common file operations? Okay, cool. Okay, the book talks about a couple complications that we may get to eventually. Mainly that it's difficult to implement things whenever, especially like open and close. I'm surprised actually it doesn't have close on this list. I guess it's kind of the obvious analog to opening a file, but closing a file is also an operation. So this is just basically updating or releasing the file handle and updating OS state. So Here we would do things like if we have a count of open files, if we have anything in terms of reading or writing locks to ensure that we don't overwrite changes that another system is or another user is making. We might have some special stuff in terms of updating the state for files. So then we have a couple other pieces of information that the OS associates with this. So we have the file pointer, which we just talked about. This is the offset, or I guess this is something that the OS maintains a last read and last write position, so that the user knows where they're working in the file, and so that the OS can continue reading from a certain point or continue writing from a certain point. Maintains an open count so that we know how many current processes are currently opening this file. So it may have a table of open files, and we want to reuse some of those spaces instead of instead of creating a new one every time. So we maintain a count of processes that are using the file so that we know when it's safe to remove a file from other OS structures. We talked about this, it's been a little bit, does anyone remember, are files associated with processes or with threads?
Processes?
Yeah. Yes, I know it's been a bit, but we want to keep in mind that the process has a list of open files. Every thread within the process shares that list of open files. So this is all per process stuff. When we open a file, when we close a file, that's all happening for the entire process rather than just for a single thread within that process.
Was that part of the, oh, sorry.
No, go ahead, go ahead.
Was that part of the PCB? Or?
Yeah, that would be part of the process control block. So that would be the open files. Yeah. Yeah, it's been months at this point probably since we talked about that. So yeah, so this is all part of the PCB, and yeah, this is not shared within the thread specific information. So keep that in mind as we go forward that we're talking about processes accessing files at this point. And then we have the location of the file. This is where it is in physical space. Kind of repeated from earlier, and access mode. So this is usually whenever a process opens a file, we get read, write, and binary usually. So we can look at the open system call and see what the flags that are allowed are read only, write only, read, write. And then we have all of these extra things that we can do, like create the file or not create the file. So this is like the append flag. If we want to only append to a file, we can not create it. We can create a file if we're trying to append, but we're not sure if it's there. So there are a number of different flags that we can pass in. You can write as binary data or as strings if you're working with something like C. So these are the things that the OS would have to maintain about a file: is how are we accessing it? Should it be doing anything special when it writes or reads to or from that file? So then, quick discussion question. Can we open the same file with different programs at the same time on Windows and on Linux? And can we edit the same file at the same time on Windows and on Linux? So go ahead and if you want to disperse into your groups for a minute or two while I get a drink, go ahead and chat about this for a minute. Okay, so I think everyone had some good answers. So yeah, this is sort of hitting on the mandatory versus advisory locking. So you can't edit the exact same file on Windows. You know, if you're editing reading, so reading is always okay. Writing is managed by the OS in Windows. So it will either, you know, create another copy of the file that you can write to two individual different copies, or if you are trying to edit the same copy of the file, it'll prevent you from doing that. So like if you have something open and you've made changes to it, and then you try to download a new copy and overwrite it, it'll usually have this warning that, like, you know, can't overwrite this file because someone else is using it, right? Whereas on Linux, writing is managed at the application level in Linux. And so you can write to the same file as long as the application can handle it. So like if you've got two instances of Emacs open, Emacs will like try to handle the updates that have happened to the, you know, it'll ask you to help it a little bit sometimes by saying like, do you want to steal this file? Do you want to reload changes from the system? But it sort of handles the locking of that file on its own, and therefore the updating of the file. So that's what I was sort of looking to get at there, is the sort of mandatory and advisory locking stuff. I have this list of common file types in here mostly as a reference. Obviously, these are different. You should have, you know, come into contact with some of these, but it's really just here, you know, as a reference. I don't want to go through any of these unless people have specific questions about them. And again, these are just ways for the user to look at and understand what this file is. You know, so the actual structure of the file is what's important here. So, you know, if you have an HTML document, you need to have the, like, you know, the HTML tags like HTML and, you know, head and body and all that sort of good stuff, right? But if it's not structured that way, then when you try to open it up as a web page, it's not going to work properly. So it's application specific what these are structured as. And same deal for like executables, right? We have specific formats that executables have to be in so that when we click on them, or when we do /executable name in Linux, the, you know, system knows how to run that program and where to put things in memory and how to load it. So all of these are just specific formats that we have to deal with. But, you know, those are not really something that we can, you know, dive into every single one of these. It's just, you know, it's all application specific stuff anyways. So then the question is, should the operating system handle the different types of files, or should that burden be left to the application? What do we think, and why? So go ahead and bounce back into your groups, chat about it for a second, and then we'll finish up there. So I'll give you a second to chat, and then we'll come back and then finish up. Okay, so we're out of time here, so I will fill in the answer. But I think everyone had the right idea that yeah, it's probably best to let the applications handle most of these file types, and maybe have the OS at most handle a couple very common things like text files and executables or things like that. So great work. Again, let me know if you have any questions on the assignments or on the exam. I am available for EI on my EI calendar, so that's tinyurl.com/Delosier APPT. I think is still works. Yeah. So if you need EI on any of these things, please let me know, or send me an email if you don't fit into one of those slots. So I will see you on Wednesday.